Hi, this is Karthikeyan. So, in the module 3, regarding D block elements, what we are going to discuss means chemical properties. Chemical properties we are going to discuss. Chemical properties. Okay. So, in the chemical properties, what you are going to discuss means, see here. So, in this, we are going to discuss about variable oxidation states, reduction potentials, standard reduction potentials, standard reduction potential, and chemical reactivity, how it is uh, related with each other, and as well as what are the magnetic properties of these transition elements, and the crystal field splitting in octahedral complexes as well as in tetrahedral complexes, and formation of colored ions, formation of colored complexes, formation of interstitial compounds, formation of alloys, and how they will show catalytical property. These are all points we are going to discuss here. Okay. Now, the first thing we are going to discuss, that is variable oxidation states. Variable oxidation states. If you carefully observe this picture, what you can able to see means, see here. So these D block elements exhibits variable oxygen states. Why it is? Why these are? What is meant by first of all variable oxygen state? Variable oxygen means more than one oxygen state who will exhibit me. That is called as variable oxygen states. More than one oxygen number, which species will exhibit, that is called as variable oxidation states. Here, these D block elements not only ns electron, it's n minus 1 d electrons also participating here. That's why here they were exhibiting variable oxidation numbers. Okay, now see here one more thing. And if you carefully observe here, what are the variable oxygen states? If you see here, see scandium plus 3 is the oxidation number, zinc plus 2. These two are not exhibiting any variable oxygen states. Many number of oxygen states they are not exhibiting here. Remaining all titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper are exhibiting. So titanium, if you see means titanium, what is the stable oxygen state or common oxygen? Stable and common is plus 4, this is plus 4. Okay, next in case of vanadium this is plus 5. In case of chromium this is plus 3 and as well as plus 6. In case of manganese this is plus 2 and plus 7. In case of iron plus 2 and plus 3. In case of cobalt plus 2 plus 3. In case of nickel plus 2. In case of copper plus 2. In case of zinc again it is plus 2. Okay, these are the stable oxygen state exhibited by this D block, especially 3D series elements. 3D series elements. Okay. Next, here when you see these D block elements exhibiting. So in this D block elements, highest oxidation number only the stable one. Okay, highest oxygen state they are exhibiting here. Why? What is the reason here? Means here not only ns electron, see here not only ns electron, n minus 1 d electrons also participating. That's why in D block higher oxidation numbers are favored. But in case of p block elements, if it means because of inert pair effect, their lower oxidation numbers are favorable things. Okay, once again see in p block, because of inert pair effect, lower oxidation numbers are favorable things. In case of D block, because of participation of ns, not only ns, due to participation of nn minus 1 d electron also, here higher oxidation number is favorable. Next, coming to the point, what are the applications of this oxidation number? And one more thing here, what is the common oxidation number in all these cases? Common oxidation number in all these cases is commonly they are exhibiting plus 3 as oxidation state. Common oxidation state, common oxidation number is plus 3. Okay, so with the help of this oxidation number, what you can identify means nature of bonding. We can identify what is the nature of bonding. How can I explain this? Whenever the oxidation number will get increases means its covalent nature get increases. Covalent nature get increases. So covalent nature get increases means acidic nature get increases. Acidic nature, acidic nature. Okay, now see here, vanadium dichloride, vanadium trichloride, vanadium tetrachloride, vanadium pentachloride. If you see in these cases, this is minus 2, this is plus 2, minus 3, this is plus 3, minus 4, this is plus 4, minus 5, this is plus 5, where the metal exhibiting highest oxidation number, there it will exhibit highest covalent character. Then it's acidic, then it will have acidic nature only, acidic nature. Acidic nature we can explain, as well as its a covalent nature also will explain here. So where it is exhibiting least oxidation number, their ionic nature it will exhibits. Okay, so this is about oxidation number and its some of the properties. Next thing is, next see, nature of oxide. So nature of oxide, how can I identify? Already I told, when oxidation number get increases, its acidic nature get increases. When oxidation number get increases, covalent nature get increases. Covalent nature get increases. As a result, acidic nature also get increases. For example, see here, MnO, Mn2O3, MnO2, Mn2O5, Mn2O7. These species I took. So in these cases, if you see where the metal is exhibiting less oxidation number, like -2, this is +2, this is -6, this is +6, that means +3. +2, +3 oxidation states, there it is basic in nature. Where it is exhibiting -14, this is +14, that means +7 it will be. Where it is exhibiting highest oxidation number, there it is acidic in nature. In between these two, least oxidation number and highest oxidation number, what we are having here, -4, this is +4, -10, this is +10, that means +5, +5. These are what? These are amphoteric in nature, amphoteric in nature. So like that, with the help of this oxidation number, we can able to find out not only nature of bond, nature of oxide also we can able to find. Okay, that's about its applications, oxidation number and its applications. Next, coming to the point, objective part. Elements which do not exhibits variable oxidation number, already we discussed it. Which won't exhibits in the D block elements, which won't exhibit means here these two. What are those? Scandium, it is exhibiting +3 only. Zinc, it is exhibiting +2 only. Okay, these two won't exhibits variable oxidation numbers. Next, coming to the point, common oxidation number of D block elements. Common oxidation number is +3. Already we discussed these points. Next, coming to the point. Next is reduction potentials. What is meant by reduction potential? Reduction potential means the potential which will develops due to gain of electrons. By gaining of electrons, what potential will be occur means that is called as reduction potential values. Next, see here, what is meant by standard reduction potential values. Standard reduction potential means in their standard conditions, like see 273 Kelvin temperature, 1 atmosphere pressure, and 1 m concentration. And in these standard conditions of temperature, pressure, and concentrations, what potentials the electrode will exhibit, that is called a standard reduction potential. That means here gaining of electron will take place by the metal in these standard conditions, that is called as the standard reduction potential values. Now see here, in standard conditions, due to gain of electrons by the metal, what electrode potential they will develop, that is called as standard reduction potential values. Okay, in D block there is an irregularity in their standard reduction potentials. Okay, why it is? I will show you this irregularity, how they are exhibiting that also. So why it is exhibiting that irregularity in their standard reduction potential means because of this reason. So here they are exhibiting variable irregularity because of ionization potential values, because of sublimation energy, and because of hydration energy. Okay, so why these are exhibiting different standard reduction potential value means because of this reason. What is that? Ionization potential values, sublimation energy, and hydration energy. Now see here, if you carefully observe these standard reduction potential values of this 3D series especially, see here, we can able to see all these are from scandium to zinc, except copper, scandium to zinc, all are exhibiting negative SRP values. Negative SRP means what? They are ready to donate electron. That means they will act as good reducing agents. Scandium to zinc, all they are exhibiting negative SRP values. Negative SRP value means they are ready to donate electrons. They are ready to donate electron. That means they are good reducing agent. They will undergo they will access good reducing, they will access good reducing agent. They are donate electron to others. That means they will undergo oxidation process readily. Okay, except copper remaining all. So these irregular trends here, see, this irregular trends, why it will take place? Because of the variation in this ionization potential, sublimation energy, and hydration energy. Ionization potential, sublimation energy, and hydration energy. Because of this reason, the irregularity will take place in their standard reduction potential values. Okay, why this copper is having high positive SRP, that means plus 0.34 means, why it is exhibiting like this means, see here, actually positive SRP values who will exhibits means, we can say it is having gaining of electron, its gaining of electron which is high. Who is having highest positive SRP values, its gaining of electron nature is high, that it indicates. That means it readily undergoes reduction process and they are acting as good oxidizing agents. See, once again, see, who are having positive SRP values, they will act as good oxidizing agents, good oxidizing agents. They will readily undergoes reduction process. These things you have to remember. So why here this copper is exhibiting positive SRP values means because of this reason. See here. So see here the reaction Cu plus 2, it is readily accepting electrons. That means it is undergoing reduction process and get converted into Cu. Now, why? What is the reason behind it to exhibit positive SRP values? Because of having, see here, copper, which is in solid form, gaining certain energy and get converted into gaseous form. Okay, so solid form of these things, it's from its constant elements onwards, it is converting into gaseous atomic form. That is called as enthalpy of atomization. Its enthalpy of atomization, see, it is gaining energy, no, it is a positive only, positive. Next, see, this gaseous copper is get converting into ions. Okay, that means by using certain amount of energy, we are going to remove the electron from this copper so that it get converted to Cu plus 2 by losing 2 electrons. So here what happens? Ionization energy 1 and ionization energy 2, both are taking place. How they are taking place? By absorbing energy again. By absorbing certain amount of energy only, it is taking place. This is also again positive only. But this, see, hydration energy, hydration enthalpy, on dissolution of the Cu plus 2 into water, see here, it releases energy. Okay, exothermic in nature. Hydration enthalpy is less. Hydration enthalpy is less here. So here, because of having highest heat of atomization and highest plus 1 ionization energy 1 and ionization energy 2 and least hydration enthalpy values, here it is exhibiting positive SRP values. That is the reason. Okay, that you have to remember in your mind. So next topic, once again, see, next topic, see, standard reduction potential values and its chemical reactivity. Okay, so how these two are related with each other. Now if you see here, standard reduction potential values and chemical reactivity, when ionization energy 1 and ionization energy 2, if it is greater than hydration enthalpy, then we can say its standard reduction potential values are positive. Whenever a species standard reduction potential values are positive, then its chemical reactivity is less. Once again, see, whenever this ionization potential 1 and 2 is greater than hydration enthalpy, then its standard reduction potential values are positive. Whenever these standard reduction potential values are positive, then its chemical reactivity will be less. Next, see, whenever this ionization potential 1 and 2 is less than hydration enthalpy, then what happens here? Its standard reduction potential values will be negative and its chemical reactivity will be high. These things we have to remember in your mind. Next topic, see. Okay, next, see, that is magnetism. What is meant by magnetism? Here, how can you explain this magnetism? So magnetism we can explain with the help of these things. See, according to Bohr's atomic model, an electron, if it's revolving around the nucleus, it is having two types of spins. Two types of spins it will exhibit. What is that? Orbital magnetic momentum, spin only magnetic momentum. Orbital magnetic momentum, spin magnetic momentum. Orbital magnetic momentum, spin magnetic momentum. What is meant by orbital magnetic momentum? If electron is revolve around the nucleus, if it is revolving means around the nucleus, if it is revolving, that is called as orbital magnetic momentum. Okay. Now spin only magnetic momentum means if the electron is revolving around itself only, means that is called as spin only magnetic momentum. Spin only magnetic momentum. Okay. This orbital magnetic momentum we are indicating with the formula mu L is equals to root over L into L plus 1 EH by 4 pi mc. Orbital magnetic momentum will be given by mu L is equals to root over L into L plus 1 EH by 4 pi mc. Spin only magnetic momentum will be given by mu s is equals to root over 4s into s plus 1 EH by 4 pi mc. Okay, so overall for this electron, how can you find out magnetic momentum? Mu is equals to it is a sum of orbital magnetic momentum and as well as spin only magnetic momentum. So mu is equals to mu L plus mu S. So mu is equals to, how can you write mu is equals to, we can write this one as L into L plus 1 EH by root over L into L plus 1 plus root over 4s into S plus 1. So if you'll take EH by 4 pi mc common. Okay, so like this we can express. So here charge of electron, Planck's constant, 4 pi value, mass of electron and as well as velocity of electron, if you substitute means you will get this value as 9.273. Okay, so how much you will get? This is nothing but it is equals to 1 Bohr magneton actually. 1 Bohr magneton is equals to 9.273 into 10 power minus 24 joule Tesla. This is joule Tesla. Otherwise 9.273 into 10 power minus 21 erg gas. This is erg gas. Erg gas. Okay. So that is the value of this 1 Bohr magneton. Now see, actually what will happens here, whenever ligands will approach the center metal atom, okay, see, since this is a ligand, if it is approaching the central metal atom, then what happens here, see, this mu L, orbital magnetic momentum will be get arrested. It won't take place. That is called as quenching of magnetic momentum. Quenching of magnetic momentum. See, that is called as quenching of orbital magnetic momentum. Once again, see, in the complexes, whenever this ligand will approach us towards to the central metal atom, okay, the central metal atom orbital magnetic momentum will be get arrested. That is called as quenching of orbital magnetic momentum. So in that case, what happens? Only spin only magnetic momentum will works. So mu is equals to what will be here? See, root over 4s into s plus 1 Bohr magneton. This is the formula we know. Okay. Now see here, already we know that S is equals to what? Spin only magnetic momentum. If one electron is revolving means S is equals to, how can you express this? We can express that. 1 second, wait. So we can express that this one as S is equals to for one electron, it is 1 by 2. 1 electron. For 2 electron, it is 2 into 1 by 2. For n number of electron, it is n into 1 by 2 we can write. So if you substitute this value, mu s is equals to root over 4 into n by 2 into n by 2 plus 1. So here we can write that is equals to root over 2n into n plus 2 by 2. Like this we can write right now. So finally, how can you express this mu s value? Means, see here, mu s value we can write that mu s is equals to root over n into n plus 2 Bohr magneton. Like this we can express. This is very, very important formula we are having. In order to find out the magnetic momentum of any complex compounds, we have to use this formula, spin only magnetic momentum root over n into n plus 2 Bohr magneton. Okay, for example, see here. For example, see here, if number of unpaired electrons are 1, number of unpaired electron 1, then its spin only magnetic moment will be mu is equals to root over 1 into 1 plus 2. That means what? This is root 3. Root 3 value, how much? This is 1.73. 1.73 Bohr magneton. Okay, if it is two unpaired electrons are present in that particular center metal atom of the complex, means its mu s is equals to root over 2 into 2 plus 2, 4 into 2. Okay, root 8, this is root 8. Root 8 means how much? This is 2.83 Bohr magnetons. 3 unpaired electron pair means mu s is equals to root over 3 into 3 plus 2, which is equals to, this is 5, this is root 15. Root 15 means this is 3.87 Bohr magnetons. 4 unpaired electron present means, see here, mu s is equals to root over 4 into 4 plus 2. That means here 624, root 24 is equals to, we'll get here 4.87 Bohr magneton. Okay, next see, if 5 unpaired electron present means mu s is equals to, we can say at root over 5 into 5 plus 2. That means here 7, that is root 35. Root 35 means this is 5.91 Bohr magnetons. Sometimes they will give this value, magnetic momentum value they will give, and they will ask how many number of unpaired electrons present. This is easy, see. If it is 1.73, if it is 1.73, okay, then one unpaired electron will be present. If it is 1.73, one unpaired electron. If it is 2.83, two unpaired electron. If it is 3.87, three unpaired electrons. If it is 4.87, four unpaired electrons. If it is 5.91, this is five unpaired electrons. Like that, in easy way, we can identify the number of unpaired electron present in the center metal of the complex. Is it clear? I hope you understood up till now what I explained. Next topic is, next see here, different magnetisms we have to discuss here. In that, diamagnetism, paramagnetism, ferromagnetism, and antiferromagnetism, and ferrimagnetism. These points we have to discuss here. First of all, diamagnetism. What is meant by diamagnetism? So substances which are repelled by magnetic field means that substance will exhibit this diamagnetism property. So which substance will be repelled by the magnetic field, external magnetic field, means those substances are called as diamagnetic substances. Why it will arise? Because of what reason it will arise? It will arise because of paired number of electrons. See here, all paired number of electrons. Because of this paired number of electrons, here it will be repelled by the external magnetic field, so that they are diamagnetic in nature. Here mu becomes, they are not at all attracted by the magnetic field, so that mu is equal to 0. It won't depends on temperature. And what are the examples? Sodium chloride is the example for diamagnetic substance. Titanium oxide is a good example. Vanadium pentoxide is a good example for diamagnetic substance. Next, paramagnetism. Paramagnetism means nothing but substances which are attracted by the magnetic field, means, okay, which substances are, which complexes are attracted by the external magnetic field, means those substances are called as paramagnetic substances. Why they will exhibiting this paramagnetism, otherwise why they are attracted by the magnetic field, means because of having at least one unpaired electron. See here, at least one unpaired electron is present here. Due to presence of this at least one unpaired electron, they are attracted by the magnetic field. Okay, that is the reason. Next here, definitely they will exhibit certain magnetic momentum, mu is equals to certain value, mu is equals to high. Next, if you see here, copper, iron, titanium oxide. Copper, iron, titanium oxide. If you see me, these and all, Cu plus 2, Fe plus 3, and titanium oxide will comes under this paramagnetism. Next, coming to the point, ferromagnetism. Substances which are attracted strongly by the magnetic field, means those are called as ferromagnetic substances. Ferromagnetic substances. Substances which are strongly attracted by the magnetic field. See here, these are attracted by the magnetic field only. Here, strongly attracted by the magnetic field. Why these are strongly attracted by the magnetic field, means because of having all unpaired electron and showing same spins, parallel spins they will show. because that reason strongly they are attracted by the external magnetic field here. Okay, here mu will be very high. Mu will be very high, and we can find out this mu value with the help of root over n into n plus 2. Which substance will act as a ferromagnetic in nature means iron, nickel, chromium dioxide. Very, very important. Iron, nickel, chromium dioxide shows this ferromagnetic property. Next, anti-ferromagnetic properties. Substance very strongly repelled. Here, see, this is repelled by magnetic field. Diamagnetic substances are repelled by magnetic field means here these are strongly repelled by external magnetic field means those substances are called as anti-ferromagnetic substances. Okay, so why it happens like this? Here, one of the electron magnetic field will be compensated by another electron magnetic field. That means each and every electron magnetic field will be compensated with another electron. Okay, due to opposite spinning of electron here, it will be greatly repelled by the external magnetic field. Those are called as anti-ferromagnetic substances. Here mu is equals to 0 only. And what are the substances that are example for this anti-ferromagnetic property means MnO, MnO2 and Fe2O3. Okay, these and all are the example for anti-ferromagnetic properties. Next is ferrimagnetism. What is ferrimagnetism? This is a special case of anti-ferromagnetism. This is a special case of anti-ferromagnetism. Okay, so here magnetic momentum will be not equal to 0. Certain magnetic momentum definitely exhibits. It occurs due to unequal spinning of electrons. See here, there is no equality. There is no parallel spins also. Unequality. Some will be moves in, will rotate in clockwise direction means some will rotate in anti-clockwise directions. So inequality in their spinning of electrons. Okay, because that reason what magnetism will be exhibiting that is called as ferrimagnetism here. Okay, next topic is next see here crystal field splitting. Crystal field splitting, if you see means here the splitting of d orbitals in their transition elements in its complex compounds will be two ways. In octahedral complexes, the splitting will take place. In tetrahedral complex also, the splitting of d orbital will take place. This is about central metal atom I'm discussing here. Central metal atom, d orbital will splits because of ligand orbital approaching. Okay, first of all, we will see how the d orbitals will be. So d orbital will be, it is divided into two ways: triply degenerated d orbitals, doubly degenerated d orbitals. Triply degenerate means that is T to Z, doubly degenerate means that is easy. Okay, so triply degenerated orbitals are present in between the axis. This is very important. In between the axis, triply degenerated orbitals are present in between the axis. Doubly degenerated, that means easy orbitals are present along the axis. Triply degenerated orbitals, what are those? dxy, dyz, dzx. Doubly degenerated easy means dxy, dx square y square and then dz square. These two are doubly degenerated orbitals. Okay, these are present along the axis. They are present. Okay, now in octahedral complex we'll see how the splitting will take place. For example, see here in octahedral complex, central metal atom will be like this and its d orbital will be like this. Here in octahedral complex, all the ligands are approaching along the axis only. They will approach towards the central atom. Along the axis, what orbital we are having? See, along the axis here, along the axis we are having two orbitals, two d orbital. What are those? Dx square y square and then dz square, and dz square. These are present along the axis. Okay, so because of presence of these easy orbitals dx square y square and dz square along the axis, so ligand orbitals nothing but they are orbital nothing but electrons. That means they are negatively charged species, right or not? So these negatively charged species, when they are approaching towards to d central metal atom means in there these easy orbitals also present in the same wave. So these easy orbitals and ligand orbitals, they will repel with each other. So they will experience highest repulsion. Who easy orbitals will experience highest repulsions, so they will occupy highest energy level. This is easy level. Okay, so these T to Z, three means triply degenerated orbitals are experiencing less repulsion force with the ligand orbitals, so that they are occupying lowest energy level, that is T2Z level, T2Z. Okay, now if you see here, this is the gap between these two, EZ and T2Z level. In between these two, the energy gap, this is that we are indicating with the delta naught. Here, from here to here, how much energy difference will be means when compared this one, this is how much greater this is. See, this is 3 times greater, plus 3 by 5. That means we can say as plus 0.6. Okay, delta naught, otherwise 6 differential quanta is high. When compared to EZ, how much it is less? This is minus 2 by 5. Minus 2 by 5. That means how much? We can say that this is minus 0.4 delta naught. Otherwise, we can say as plus 4 dq differential quanta. Sorry, minus 4 differential quanta it is exhibiting. Okay, that is the energy difference between these two. From here, this is crystal field splitting energy gap. From here to here, the energy difference is plus 6 dq. From here to here, the energy gap is minus 4 dq. Okay, so when it will take place? So towards the central metal atom, whenever strong ligands are approaching, means when strong ligand approaching towards the central metal atom, the splitting will take place maximum like this, The splitting will take place maximum like this. Whenever weak ligands are approaching, means towards this, then what happens? Minimum splitting only takes place. See, here also same. EZ orbital will occupy higher energy level, T2Z will occupy lower energy level, but the splitting gap is minimum only. Okay, that is the difference between these two. In case of strong ligands, splitting is maximum extent it will take place. In case of weak ligand, the splitting will take place minimum extent only. Okay, so because of having highest energy gap between these two, okay, maximum extent of splitting here. Here, whatever the electrons we have, these are all electrons. Okay, these are all electrons. First, they will pair ups. Okay, first they will pair ups, and then remaining electron will be enters into EZ level. After pairing only, they will enter into EZ level. But here, because of less energy gap between them, here see, after filling this with one electron, immediately it will jump to next level here. Here pairing will take place and then distribution. Here distribution will take place and then pairing. Okay, that is the difference we have to understand in octahedral complexes. Okay, next in tetrahedral complex, what happens? We'll discuss here. In tetrahedral complexes, central metal atom. This is tetrahedral complex. In tetrahedral complex, see, central metal atom will be like this. Ligands will approach in between the axis. This is very important. In between the axis, they will approach. Here. So in between the axis, what orbitals we are having? In between the axis, we are having dxy, dyz, dxz. These three orbitals are present in between the axis, so that they will experience the highest repulsion forces. So that in tetrahedral complexes, T2Z will occupy highest energy level. Okay, this is T2Z, and EZ will occupy lowest energy level. Next here, this is in case of strong ligand. If strong ligand will approach us means towards central atom, the splitting will be again maximum. If weak ligand will approach us to the central metal atom means, then here also the splitting will be same, T2Z only in the upper energy level, in lower energy level EZ only, but here minimum splitting only will take place. That is the difference you have to understand. Here also same. First of all, electrons will be, whatever the electrons we are having here, these electrons will come. These electrons, for example, these electrons are present here. First of all, these electrons will be pair up. After pairing all these electrons, next the electron will jump here, 4, 5, 6. Here 1, 2, because of less energy gap in between these two, 1, 2, 3, 4, 5, and then pairing, distribution and then pairing. So that is the trend that will take place in case of octahedral complex as well as in tetrahedral complexes. Next thing is see, next is formation of colors. How it will form colors. For example, here we are having certain number of electrons. Okay, so that electrons I'm going to distribute here. Okay, now what happens? These electrons will absorb energy from the visible region. See, from the visible region, from visible region it will absorb certain color and it will go to the next excited level here. There it will feels instability again, it wants to come back to the ground state. Means what I have to do, the absorbed energy it releases in the form of different colors. Okay, different light colors. For example, see, violet color, if it absorbed means this electron, in order to excite into the highest easy level, if it absorbed violet color means while coming to the ground state it releases yellow color. This is complementary color. Okay, indigo color, if it absorbs means yellow green color it releases. Blue green color, if it absorbs means red color it releases. Green blue color, if it absorbs means orange color it releases. Yellow color, if it absorbs means violet color it releases. Yellow green color, if it absorbs means from the visible region indigo color it releases. Orange color, it absorbs means green blue color it releases. Red color, if it absorbs means blue green color it releases. Green color, if it absorbs means purple color it releases. Like this, from the visible region this electron will absorb at one type of color, and after reaching to the excited level again it want to come to the ground state. Means it releases the colors in the form of complementary ways. Okay, in the complementary ways, that means opposite colors it releases here. Okay, that is the formation of colors by the complexes. That is the reason for the formation of colors by these complexes. Next topic, see. So next concept is about potassium permanganate. Some important compounds we are having here, potassium permanganate. One is potassium permanganate, next one is potassium dichromate. So preparation of potassium permanganate, how it will be done? So by taking pyrolusite, this is nothing but pyrolusite, very important compound. Pyrolusite MnO2 on reaction with the base, then it will form potassium manganate, which is a dark green color, potassium manganate. That potassium manganate in the presence of acidic medium we get converts into potassium permanganate, KMnO4, purple color potassium permanganate. Okay, so that is a preparation of this potassium permanganate from its pyrolusite MnO2. Next, what is physical properties? Physical property means manganese having sp3 hybridization, and it is exhibits tetrahedral shape, and its complex manganese exhibits +7 oxidation number, +7. Its color is purple color. Actually, if it is in +7 state means it should not exhibit any color. Why? Means see here, manganese atomic number is 25. Its electronic configuration is argon 3d5 4s2. That means complete all its electron gone. It lose its electron, 7 electron it lost. When it lost all these 7 electrons, then its electron configuration will be in its +7 state, argon 3d0 4s0 only. No color it should not exhibit here. But because of charge transfer from this oxygen to manganese, what is this? Very, very important point. Due to charge transfer from oxygen to manganese here, it is exhibiting purple color. That is the important thing you have to remember here. Okay, once again, see, manganese having sp3 hybridization, it's a tetrahedral shape, and it's a +7 state, it will exhibit in its potassium permanganate state, and it's a purple in color. Why it is exhibiting purple in color even though it is not having any d electron? Means because of charge transfer from oxygen to manganese. That is the reason. Next, see its chemical properties. So this potassium permanganate will oxidizes this iron Fe+2 ferrous into ferric. Okay, next it will oxidize iodide into iodine. That is important thing you have to remember. Iodide into iodine. Here ferrous into ferric. Like that will oxidizes. Next, oxalate ions. Oxalate will be get oxidizes into carbon dioxide by this potassium permanganate. These are the chemical properties of this potassium permanganate. Next is about potassium dichromate. Next, see here, the next important compound is potassium dichromate. Potassium dichromate. How it is prepared? For example, see, iron chromate we are taking here, iron chromate, that is going to react with sodium carbonate, so that we will get here sodium chromate, Na2CrO4, sodium chromate we are getting. This sodium chromate, we are going to react in the presence of acidic medium, means it will get converts into sodium dichromate. This sodium dichromate, now it is react with potassium chloride, means it will form orange red color potassium dichromate K2Cr2O7. Once again, see, iron chromite we are taking, and we are going to react with this sodium carbonate, means we are getting here sodium chromate. This sodium chromate, in the presence of acidic medium, it will get changes into sodium dichromate. This sodium dichromate on reaction with the potassium chloride, it is get changing into orange red color potassium dichromate. This is a preparation of potassium dichromate, and its physical properties see here. Here in between chromium, see chromium and oxygen, here all these oxygens see here. So chromium, around these three oxygens, around this chromium also three oxygens we are having. So in between two chromiums, one oxygen is present here as in the form of a bridging atom. Now in between these chromium and oxygen chromium, the bond angle is 126 degrees, 126 degrees. Okay, and the bond length between oxygen and chromium is 179 picometers. Bond length between chromium and oxygen is 163 picometers. Okay, so this is the physical property. In that physical property, structure of potassium dichromate, if you see, means once again see, in between oxygen and chromium 179 picometers, in between chromium and oxygen 163 picometers, in between chromium, oxygen, chromium, the bond angle is 126 degrees. This is about its structure. Chemical properties, if we see, means potassium dichromate will changes potassium iodide into iodine. Potassium dichromate will oxidizes potassium iodide into iodine. Next, potassium dichromate will converts hydrogen sulfide or oxidizes hydrogen sulfide into sulfur. Potassium dichromate will convert sulfur dioxide into potassium sulfate. Like that, it will get oxidizes. These are the important points we have to remember. And then very, very important reaction is test for chlorine. That is chromal chloride test. Chromal chloride test. What is that? Potassium dichromate, when reacts with, in the presence of acidic medium, when it reacts with chlorine contained compounds, then it will form orange red color chromal chloride. Orange red color chromal chloride will get produced. Formation of orange red color chromal chloride indicates that that particular substance consists of chlorine as one of the ingredient. So this is chromal chloride test. Next, about the next topic. Next topic is about F block elements. So F block elements. F block elements, if you see, means here. So these are the lanthanoids. Lanthanoids. These are called as actinoids. This is also called as 4F series, and this is also called as 5F series. Lanthanoid consists of, see, lanthanoid will start from lanthanum to lutetium, lanthanum, cerium, praseodymium, neodymium, promethium, samarium, europium, gadolinium, terbium, dysprosium, holmium, erbium, thulium, ytterbium, lutetium. From 57 to 71, these are all called as lanthanoids. Okay, these are kept in 4F series. Why means here the differentiating electron enters into 4F level. That's why it is called as 4F series. So actinoids, actinoid means from actinium up to lawrencium. These are all called as actinoids. See, actinium, thorium, protactinium, uranium, neptunium, plutonium, americium, curium, berkelium, californium, einsteinium, fermium, mendelevium, nobelium, lawrencium. These and all comes under actinoids 5 series. Due to differentiating electron, due to entering of this valence electron into the 5F orbital, it is called as 5F series now. Okay. This is about the brief introduction about these F block elements. Its general electronic configuration efficiency means N-2 F0 to 14, N-1 D, N-1 D, 0 to 2, NS2. Here, all ultimate, penultimate, and anti-penultimate shells electrons will participate in the bond formations in chemical reactions also. Okay, now see here N-2 F0 to 14, due to entering of valence electron or differentiated electron into F orbitals. These are considered as F block elements. Okay, these are kept in F block elements. Okay, next Seema. Next, if you see here, F block elements are widely divided into two parts. Already I told lanthanoids and actinoids. That means 4F series elements and 5F series elements. Lanthanoids and actinoids. These are lanthanoids and these are actinoids. What its general configuration? See, N-2 F0 to 14, N minus 1 D0 to 1, N minus 1 D0 to 1, NS2. Actinide's general electronic configuration N minus 2, 0 to 14, N minus 1 D, 0 to 2. See the difference between these two. This is 0 to 1 means here 0 to 2 and NS2. Remaining all things are same only. Okay, above general electronic configuration only we'll write here. So lanthanide belongs to what? It is belongs to third B sixth period. Third B sixth period here. Okay, from lanthanum 57 to hafnium 72 are called as lanthanoids. Next, see here, why these are kept in this 4f series only? Why means here differentiating electron enters into 4f orbital. That's why these are kept in 4f block. Okay, 4f series especially. Here these are called as rare earth elements. These are rarely found in earth crust. That's why these are called as rare earth elements. These are non-radioactive in nature except promethium. Except promethium, remaining all are non-radioactive. Coming to the point, actinoids. These are belongs to third B seventh period, from actinium to rutherfordium. Okay, here the differentiating electron enters into 5f orbital. That's why these are called as 5 series elements. These are man-made elements generally. Many of the elements are radioactive in nature. Okay, this is about F block elements. Coming to the point of stable electronic configuration, see F0, F7, F14. These electronic configurations, wherever we can find them, those are all stable electronic configurations. Next is basic strength efficiency means as the size of atom get decreases here because of lanthanoid and actinoid contractions, what happens here? Covalent nature get increases. Covalent nature. When covalent nature get increases, what happens? Basic nature get decreases. Basic nature decreases, acidic nature get increases. Acidic nature get increases. As a result, see here, lanthanum hydroxide, lutetium hydroxide, which is having highest basic nature means lanthanum hydroxide is having strong basic nature, lutetium hydroxide is having weak basic nature. Okay. Next, solubility efficiency means as the size of atom get decreases, the bond strength also will get increases. Bond strength get increases. So that which is having large size means that is easily soluble. Its bonds also easily breakable also. That's why lanthanum carbonate is easily breaks its bonds due to this huge distance between the nuclei. So readily soluble in nature. But lutetium carbonate, it won't soluble because of small size due to having strong intermolecular attraction forces. Here it is less soluble in nature. Next, colors efficiency means the same trend in D block elements of what trend we expect, the same trend here it will follows. Generally, electron is present in the ground state. It absorbs energy from the visible region. So it will exit, it will go to the next excited level. After reaching to the exit level, there it will feel instability. Again, it will come to the ground state here. While coming to the ground state, what will do? It releases the energy in the form of complementary colors. Okay. So because of that reason here, it is exhibiting colors. And which won't exhibit any color here, see, which is having in which f orbital 0 and 14, that means completely filled, and which is completely vacant, that configuration do not exhibit any colors here. So extraction, how can you extract this? All lanthanides are extracted from its monazite sand. Monazite sand. All lanthanides are extracted from its monazite sands. Next, we are going to discuss about this actinoids. So actinides, if you see, means here, see, the differentiating electron enters into 5f orbital. That's why these are called as 5 series elements. And its general electronic combination n-2 f 0 to 14, n-1 D 0 to 2, and NS2. Next, its atomic and ionic radius efficiency means gradually it get decreases due to actinoid contraction. It will get decreases due to actinoid contraction. Basic strength also same. M2O3 and M2O5 if you compare means. So whenever the oxidation number get increases, see here minus 10, this is plus 10. That means this is plus 5. Okay, this is plus 3. So plus 3 and plus 5 if you compare means which is having highest covalent nature, this is having highest covalent nature, so that its acidic nature gradually get increases. Okay, next colors if you see means actinide shows colors in their plus 3 and plus 4 states. Okay, that's about actinides. And accident, if you see some of its properties, they are paramagnetic in nature. Paramagnetic in nature. They are paramagnetic in nature. They are electropositive. Next, they exhibit less ionization potential values. They have high melting and boiling point also. Okay, so this is about actinides. Next, we are going with this objective part. See here, next last module, objective part we are going to discuss here. Module 3, objective part. So in module 3, objective part, if you see, means magnetic moment of FeS2O 6 times SO4 is given by 4 into 4 plus 2 Bohr magneton. So this is correct or not? We are going to check out. In the above complex, iron has 4 unpaired electron. They are saying here. We'll check out. This is -2. This is +2. Okay. So iron is in the form of +2 state. Iron 26, and this is argon 3d6 4s2. After losing these 2 electron from here, okay, 3d d orbital having how many electron? We'll check out here. 1, 2, 3, 4, 5, 6. See here, 4 unpaired electrons. 4 unpaired electron means mu s is equals to root over 4 into 4 plus 2 Bohr magnetons. Okay, so this is correct. So assertion is correct as well as reason also correct explanation. Okay, next bit is, next see here, the spin only magnetic momentum in Bohr magneton of Na plus 2 in aqueous solution would be 2.84 Bohr magnetons. The metal ion has 2 unpaired electrons. Whether these two, assertion and reason, whether they are correct or not, we are going to check out here. Now see here, so nickel, whose atomic number is 28, okay, and its electronic configuration will be argon 3d8 4s2. So nickel is in the form of +2 state. Nickel is in +2. That means these 2 electrons will last, means then it is equals to argon 3d8 4s0. 3d8 means see here 1 2 3 4. That means see here 1 2 3 4 5 6 7 8. That means how many unpaired electrons? Only 2 unpaired electrons. 2 unpaired electrons, mu is equals to root over 2 into 2 plus 2. That means 4 root 8. Root 8 means that is nothing but 2.84 Bohr magnetons, right? See here, assertion, magnetic momentum of Na plus 2 ions can be very close to that of Na plus 2 ions. Both metals have equal number of unpaired electrons. Magnetic moment of these two are exhibiting same, they are saying here. So we'll check out nickel plus 2. Okay, nickel plus 2 means, so nickel plus 2, that means we can write this is 28 atomic number, argon 3d8 4s0. 3d8 4s0 means, see here, before also I explained the this same bit, 1 2 3 4 5 6 7 8. That means 2 unpaired electron only we are having, 2 unpaired electrons. We'll check out titanium also, titanium plus 2. So titanium plus 2 we see means here, see titanium plus 2. So that is nothing but argon, titan is 22, 3d2, 4s2. So if these 2 electrons will last, means then the electronic configuration will be, see here 1 2 3 4 1 2. That means here also it is having same number of unpaired electrons, right? So magnetic moment of Na plus 2 and as well as this one titanium plus 2 also same. Why? Both metals have equal number of unpaired electrons. So both assertion as well as reason are correct, and the correct explanation for assertion also. Next bit we are going to see here. See, now look at this question. When KMnO4 reacts with acidic body FeSO4, then some of the options they given here, the right option we have to choose. What is the correct option? First of all, we'll see the reaction, what happens. See, so whenever potassium permanganate reacts with this FeSO4, that means ferrous sulfate, means in the presence of what sulfuric acid, means in the presence of acid, then what happens, see here, will form potassium sulfate and MnSO4, and then see here Fe to SO4 thrice. Now see here, from iron sulfate to Fe to SO4 thrice. Okay, here what happens, from potassium permanganate to MnSO4, what happens, that you have to see here. See, this is -8 actually, this is +1, so this is +7 state. Now see here, this is -2, this is +2 state, +2 state. +7 to +2, decrease in the oxidation number. +7 to +2, decrease in the oxidation number. That means what? By gaining of electron, the +2 state, gain of electron is nothing but reduction. Reduction, this is reduction. Otherwise, we can say potassium permanganate get reduced, we can say. Here see FeSO4 -2, this is +2, whereas Fe +2 state, from that state to it went see SO4 -3, -6, +6, that means +3. +2 to +3, increase in the oxidation number. That means loss of electron. It definitely undergone oxidation. Okay, otherwise we can say it is get oxidized, we can say. Okay, so by seeing this one, what you can explain means FeSO4 is oxidized, FeSO4 get oxidized, and KMnO4 get reduced. This option we can select and we can express like this. Okay, next bit. Next question, see here. The number of moles of potassium permanganate that will be needed to react with 1 mole of sulfite ion in acidic solution, they are asking. First of all, see this reaction. Once again, see here. See here, MnO4 minus is reacting with SO3 minus 2 in the presence of H plus. And that means in acidic medium, it will get changes into Mn plus 2 plus SO4 minus 2 plus H2O. So if you balance this equation, means this 2 moles and 5 moles and this 6 moles, 2 moles and this is 5 moles and this is 3 moles. Okay, they are asking the number of moles of potassium permanganate that will be needed to react with 1 mole of sulfite ion. Okay, so 2 moles of potassium permanganate required 5 moles of sulfite ions. Okay, with for 1 mole of this sulfite ion, how many moles of potassium permanganate is required? 1 into 2 by 5 moles of MnO4 minus. That means 2 by 5. This is correct answer. Okay. Next, see here, the product of I minus with MnO4 minus in alkali medium is they're asking. See here, potassium permanganate reacts with potassium iodide in acidic medium as well as in alkali medium. The difference I'll explain. See, in acidic medium it will form K2SO4, potassium sulfate, MnSO4 plus I2 plus H2. This potassium iodide is get converted into I2, means in this case is get converted into potassium hydroxide plus MnO2 plus potassium iodide KiO3. In this manner it will get changes. That is the difference in these two reactions. See carefully, the product of I minus with MnO4 in alkali medium, this they are asking, alkali medium. So I'm explaining here the difference between acidic medium and alkali medium. In acidic medium, it is get changing into K2SO4, MnSO4 and I2. In basic medium or alkali medium, it get changes into KiO3. That is the difference you have to understand here. Okay, next question, see the number of moles of potassium dichromate that will need to react 1 mole of hydrogen sulfide in acidic medium, they're asking. So if you see this one, the reaction, see here K2Cr2O7 plus 4H2SO4 plus 3H2S gives rise to K2SO4 plus Cr2SO4 thrice plus 7H2O plus 3S. They're asking the number of moles of potassium dichromate that has to react with hydrogen sulfide. See the relation between these two. 1 mole of this potassium dichromate requires 3 moles of hydrogen sulfide. Okay, 1 mole of this potassium dichromate that will need to react with 1 mole of, see here 1 mole only this is. If it is 1 mole means how many moles of this one it required? 1 into 1 by 3 means 1 by 3 moles of potassium dichromate required. So this is the answer. Okay, so next question we will switch on. Next question, see here, chromyl chloride when dissolves in NaOH solution gives yellow solution. The yellow colored solution contains what they're asking. See here, chromyl chloride CrO2Cl2, okay, that is going to react with NaOH then it will form Na2CrO4 plus NaCl plus H2O. So here, if you balance this equation, means 2CrO2Cl2 plus 4NaOH gives us to Na2CrO4 plus 2NaCl plus and H2O. Okay, now see here, what is the compound that is yellow color compound will get forms here? This is the yellow color compound that will get forms, sodium chromate. Okay, so next question will switch on. Next is which oxide of manganese is acidic in nature, they're asking. See here, this is -2, this is +2, this is -14, this +14, that means +7, this is -6, this is +6, that means +3, this is -4, this is +4. Among all, which is exhibiting maximum oxidation number? This one. Oxidation number getting increased means covalent nature getting increases. Covalent nature getting increased means acidic nature getting increases. Right now, so we can say that Mn2O7 is most acidic in nature. Clear? Next question. Next question, see the magnetic momentum of an ion, it's a +3 state. +3 oxidation state is 3.85. The number of unpaired electrons, already before I explained, 1.73, 2.83, 3.87, like that means how many number of unpaired electrons? Easy to identify, I already told. Here I'm going to explain. See, from the options we can easily identify. Some of the questions from the options we can pick. See here, for example, I'm taking this √3, means three unpaired electrons I'm going to take here. So μs is equals to √n into n plus 2 Bohr magneton is the formula. Okay, so √3 into 3 plus 2 Bohr magneton means this is 5 plus 5 into 3, that is √15. √50 means 3.85 only, okay, Bohr magnetons. So we can say that this is the correct option. So 3 unpaired number of electrons will be present in that compound. Next, see here, match the following they're asking here. Scandium +3, whose atomic number is 21. Vanadium +3, vanadium 23, iron 26, copper 29. So after losing 3 electrons, its electronic configuration is 3 means 3d0, 4 is 0. Okay, vanadium if you see means 3d3, 4 is 0. Next, after losing this 3 electron, here is 3d5, 4 is 0. Cu plus 2, 3d9, 4 is 0. Here, it will exhibit 0 as magnetic momentum. This vanadium plus 2, this will exhibit 3.87. This will exhibit Fe plus 3 means, so how many unpaired electrons? 3d5. So 5 unpaired electrons, √5 into 5 plus 2, means √735 here. Okay, 5.92. 5.92. Next here, 9 means see here, 1 electron, 1 unpaired electron will be, 1 unpaired electron means here, √1 into 1 plus 2, that means √3. √3 means 1.73. Okay, so these are the things. So we can select this 13 means 3, 4, 1, 2. I think this is correct answer. Okay, right. Next question we are going to switch on. Next, see here, which of these react with potassium permanganate to give oxygen quantitatively? Okay, now see here, potassium permanganate KMnO4, if reacts with H2O2, then produce 3O2 plus 2MnO2 plus 2KOH plus 2H2O. So quantitatively oxygen will get produced with the help of this hydrogen peroxide. So this is the answer. Okay. Next, see here, CrO4 minus chromate and dichromate, pH is equals to X. Chromate is changing into dichromate, pH is X, and vice versa. Dichromate will get changed into chromate, so pH is equals to Y. Hence, X and Y are what they are asking. See here, CrO4 minus chromate is get changing into dichromate, Cr2O7 minus 2. So here, in what conditions? In acidic condition, we have to do this. So acidic condition means pH is equals to what? 6. Okay. Next, in basic medium, this will get changes into Cr2O7 minus 2, dichromate will get changes into chromate here. Here pH will be C8. Okay. So 6 and 8 will be the answer for this question. Next question, see the atomic number of the element having a magnetic momentum equal to 1.7 Bohr magnetron and its plus 2 oxygen state. So from this, I'm going to select this first option, whose atomic number is 29, copper, argon, and this is 3d 10 4s1 electron configuration will be. Okay, after losing 2 electrons, he's saying that plus 2 oxygen state. After losing 2 electrons, the configuration will be argon 3d9 4s0. 3d9 4s0. Now see how many number of unpaired electrons will be here. You see here 1, 2, 3, 4. That means 1, 2, 3, 4, 5, 6, 7, 8, 9. That means only one unpaired electron. So mu s is equals to root over 1 into 1 plus 2. That means 3 electrons. Root 3 is nothing but 1.73 Bohr magnetons. So this is correct option. Next question we will see this next question. The atomic number of transition metal is 25 and the magnetic momentum is momentum in its plus 3 oxygen state they are asking. Okay, plus 3 oxygen state. So manganese I'm going to take here, manganese, whose atomic number is 25, electronic configuration is argon, 3d5, 4s2. 2 electron lost from here, 1 electron from here, then the configuration will be 3d4, 4s0. So 3d4, 4s0. That means see here 1, 2, 3, 4. 4 unpaired electron will be present right now. So 4 unpaired electron present means here. So what is the spin only magnetic momentum? Mu s is equals to root over 4 into 4 plus 2. 4 into 4 plus 2 means here this is root 24. Root 24 means what is the value? 4.89 Bohr magnetons. Clear? 4.89. Nearly we can choose this option. Right? Next question we are going to switch. So next question is here, magnetic momentum of Mn plus 2 is 35. Mn plus 2, Mn plus 2, it is actually 25 now. So argon 3d5, 4s2. After losing these 2 electrons, see 5 electrons will be. 5 electron means mu s is equals to root over 5 into 5 plus 2. That means root over n into n plus 2 formula, Bohr magnetons. So 7 into 5, root 35. Root 35. So this is correct option. So titanium plus 4, titanium plus 4, titanium, scandium, titanium 22, argon 3d2, 4s2. All these two, the means total 4 electrons will be come out from here. It will loses means. Then what is the configuration? Argon 3d0, 4s0. It won't show any color titanium. So that this option is incorrect. 1 Bohr magneton is equals 9.273 10 power minus 24 joule Tesla. This is correct only. Secondary valency of transition metal ion is equals to its coordination number. That is also correct. So we can choose, we can go with this 1, 3, 4 are correct options. Okay. Next, we are going to discuss about. Next here, the magnetic momentum of an ion is close to 36 into 10 power minus 24 joule Tesla. The number of unpaired electrons in the ion are. It's a very good question here. See here. So what is the question? So here we can go with this root over n into n plus 2 Bohr magnetons. No, that means Bohr magneton means what the given value 36 into 10 power minus 24 joule Tesla. So here I'm going to use 9.273 into 10 power minus 24 joule Tesla. Okay. So 9.273 and 36, how much it will go? It definitely 3.88 Bohr magnetons. So root over n into n plus 2 is equals to 3.88 Bohr magneton means n into n plus 2 is equals to, we can write this one as 15 right now. I'm squaring on both sides. Then we'll get here n square plus 2n minus 15 is equals 0. So finally n value will get here 3. That means n value will be 3. The number of unpaired electrons will be 3 here. So the correct order of E m plus 2 by m values with a negative sign for successive elements chromium, manganese, iron, cobalt is. So So it's an experimental evidence. If you see here in our NCERT book, so the order they given as Mn is greater than chromium is greater than iron is greater than cobalt. Okay, so second option is correct one. So this we have to follow. Next. So next question, the number of moles of potassium permanganate that will be needed to react completely with 1 mole of ferrous oxalate FeC2O4 in acidic solution is. See here, 1 second. Okay, MnO4 minus, I'm going to take MnO4 minus plus FeC2O4, ferrous oxalate. So it is react means then it will forms Mn plus 2 is Fe plus 3 plus CO2. Okay, so here if you see, if you balance this equation, now see here, it becomes here 3 and here 5 moles and this is 5 moles. Number of moles of potassium permanganate they're asking, that will be need to react completely with 1 mole of ferrous oxalate. Okay, now see here, so 3 moles it requires 5 moles, so they're asking 1 mole. With this 1 mole need to react completely with 1 mole of ferrous oxalate. Okay, ferrous oxalate means how much it requires, 1 into 3 by 5. So 3 by 5 is, this is correct option. Next, see here, pair of ions which are having only one pair electron, one unpaired electron they are asking here. Okay, now see here, so if you see cerium plus 3 whose atomic number is 58, xenon 4f1 5d0 6s0. In a similar way, ytterbium plus 3 whose atomic number is 70 and its electron configuration is equals to xenon 4f13, okay, and then 6s0. In these two cases, see here, in these two cases 1 2 3 4 6, okay, so 1 2 3 4 5 6 7 8 9 10 11 12 13, here one unpaired electron, here also same way one unpaired electron only we are having. Okay, only one unpaired, that is cerium plus 3, ytterbium plus 3. Okay, next question we have switch on. So in which of the following lanthanides oxygen state plus 2 is most stable, they're asking here. So in which of the following means it is europium plus 2. See here, europium plus 2 whose atomic number is 63, xenon 4f7 and this is 6s2, 4f7 6s2. Okay, so if you see here 4f7 6s2, see here half filled configuration is happening. Okay, now see here 1 2 3 4 5 6 7, half filled configuration, so that's why it is most stable. Europium plus 2 state is very stable one. Okay, next see here, the outer electron configuration of gadolinium is gadolinium. Gadolinium is nothing but, see here, its atomic number 64, xenon this is 4d7 5d1 6s2. Okay, so 4f7 5d1 6s2, we will go with this option. Next, see here, a larger number of oxygen states are exhibited by an actinide than by lanthanides. The main reason being is, okay, see here, due to less energy difference between 5 and 6d than between 4f and 5d orbitals. Because of this reason only, these are exhibiting larger number of oxygen states. Okay, right, next. So the ion with maximum number of unpaired electrons, they're asking ion with maximum number of unpaired electrons. This is gadolinium plus 3. So already we discussed this in previous question. Gadolinium plus 3, if you see, means, so it is having what? 1 second, wait. So it is having what? This is having atomic number 64 and its electronic configuration is xenon. And this is 4f7 5d0 6s0. Okay, so see 7 unpaired electrons will be there, so that maximum number of unpaired electrons will be present here. Next, see here, which of the following ion is paramagnetic in nature? Paramagnetic. That means unpaired electron must be present in this. So samarium plus 3. How would you see? Samarium, if you see samarium plus 3, its electronic configuration xenon 4f5 6s0. So 4f5 6s0, if you see, means here 1 2 3 4 5. So because of having many unpaired electron, here it shows paramagnetic property. Okay, that's the end of your all these d block elements. So I hope all of you understood what I explained here. So thank you for your patience to listen my class. Have a nice day.